All right, guys, I want to do a quick introduction on trigonometry. Trigonometry is a special kind of math that relates the magnitudes of the sides of a right triangle to the angles inside. It's important to us because it's how we do vector math. We know vector math is a little bit different than scalar math, like 3 plus 4 is not always 7. For example, if I walk 3 meters to the east and then 4 meters north, of course, I've traveled a total distance of 7 meters, but that's a scalar value. If I'm looking at my displacement from where I started to where I ended up, it would be the length of this vector right here. Well, you probably notice this is a special triangle. This is a right triangle, and the side of a right triangle that's across from the 90-degree angle we call the hypotenuse. And maybe you remember the Pythagorean theorem. We can find the hypotenuse of a right triangle by doing a squared plus b squared equals c squared, where the two sides touching the 90-degree angle are A and B. It doesn't matter which one I call A, which one I call B, as long as I recognize that the hypotenuse, or the longest side, is C. So if I want to find the length of the hypotenuse, I'm just going to do A squared plus B squared, and then to get rid of the squared, I'll take the square root. So it'll be the square root of 3 squared plus 4 squared, or the square root of 25, and I end up with a magnitude of 5. So the displacement in this particular case would be 5 meters, and it's in this direction that I've indicated with the arrow. Okay, so I've got a magnitude and a direction. It's going to help us as well to do two-dimensional motion. We know that if I launch something, like let's say I launch it at 10 meters per second at a 30-degree angle. Well, the problem that we have is that our kinematic equations are only set up to go in straight lines. But we know this object that's launched at an angle is going to have that parabolic trajectory. So it's going to be moving in 2 dimensions. And that means that we can't really set up our kinematic equations in this direction because it doesn't always travel in that direction. Instead, what we'll do is we'll break this motion up into a horizontal part and a vertical part. So I'll just try to do it in 2 separate colors here. So I break it into a horizontal part and a vertical part. And the reason why I do that is because in the vertical direction, I know that the acceleration is -10, right? It's because of gravity. When I release an object or a projectile, the only thing acting on it is gravity. So it has a vertical acceleration of -10, and it has a horizontal acceleration, so I'll call that AX, of 0. Because there's nothing affecting it in the horizontal direction. So this 10 meters per second, it's great. It's what I see in real life. The object is traveling in this direction, but it's not useful to us because we need to break it into straight lines or into separate dimensions. So I can take this 10 meters per second and break it into a horizontal part and a vertical part. So the first thing I'm going to do is just identify the anatomy of this right triangle. We know that the side that's across from the 90-degree angles is the hypotenuse. The other names of these sides, the side that's touching the 30-degree angle, we call that the adjacent side, because adjacent means next to. So it's touching the 30-degree angle, and it's not the hypotenuse. And then the side that's across from the 30-degree angle, we call that the opposite. Okay. Now it turns out that the magnitude of these sides are related to the angle inside of the triangle. And we have this mnemonic device called SOH-CAH-TOA to remind us of the relationship between the sides and the angles. So the first part of that, SOH, says that the sine of an angle theta is related to the ratio of the opposite side and the hypotenuse. The cosine of an angle, so the CAH, the cosine of an angle theta is related to the ratio of the adjacent and the hypotenuse. And lastly, T, the tangent of an angle theta, is related to the ratio of the opposite and the adjacent side. So those ratios of side magnitudes are related to the angle through these 3 trig functions. And these 3 trig functions can be found on your calculator. So we have their sine, cosine, and tangent on my calculator. Okay? So what I'm going to do to break this 10 meters per second into what I call components, the x component and the y component of this 2-dimensional vector, first I'll find just the adjacent side. So if I want to find the adjacent side and I know the hypotenuse, I want to look at which trig function relates the adjacent and the hypotenuse. which I see here is the cosine. It has both the adjacent and the hypotenuse in it. So I'll start with cosine of theta is equal to adjacent over hypotenuse. And if I want the adjacent side, then I'll multiply hypotenuse to the other side. So I have hypotenuse times cosine of theta is equal to the adjacent, or 10 meters per second times the cosine of 30 degrees. Oh, sorry, the degrees should be on the inside. Okay, 30 degrees is the unit of the angle. And I'm going to put that in my calculator. So it's going to be 10 times cosine of 30 degrees, and then I'm closing the parentheses. Now I'm going to hit enter. If you don't get the same answer that I got, it's not a problem. It just means that your calculator is in a different mode. You're probably in radian mode. If you're in calculus, you probably did that intentionally. If you've never done this before, it just means that your calculator defaulted to radians. So I'll show you how to change that real quick. If I go into mode down here, I'm just going to scroll down to degree and hit enter. So if you have radian selected, you're getting the wrong answer. It's just because you're using different units. If your calculator is different than mine, show it to me in class, and I can help you change it into degree mode. We should be getting about 8.66, and that's meter per second, because the unit of the hypotenuse was meters per second. So that means that this object, when it was launched, it's traveling horizontally at a speed of 8.66 meters per second. So I could call that the initial horizontal velocity. I can do the same thing to find the vertical component. If I want to find the opposite side and I know the hypotenuse, I'm looking for the trig function that relates O and H, or opposite to hypotenuse. And I see here it's the sine of theta. So I'll start with the sine of theta, which is equal to the opposite over the hypotenuse. If I want opposite by itself, then I'm going to multiply hypotenuse to the other side. So hypotenuse times the sine of theta is equal to the opposite side, or 10 times the sine of 30 degrees is equal to the opposite side. Again, in my calculator, 10 times sine 30, close the parentheses, hit enter, and I'm getting 5 meter per second. So again, it's meter per second because the hypotenuse had units of meter per second. This is the vertical component of the initial velocity. So I could call v initial y 5 meters per second. So what I have now are the components of the two-dimensional velocity. I could use my kinematic equations in the horizontal direction using this initial velocity and an acceleration of 0. And then I could use this initial vertical velocity in the vertical direction with an acceleration of -10. And I could do my kinematic equations separately. So I'll do the blue kinematic equations, the red kinematic equations, and then at the end, I'll be able to resolve those back together to show what's happening in the real world, two-dimensional, like when this object lands, it's traveling both vertically downward and horizontally to the right. So I could find these final components, and if I want to put them back together to show what's happening in the real 2- and 3-dimensional world, then I could go back and use Pythagorean theorem to find the hypotenuse. So that's the real speed. Like if I were pointing a radar gun at this object when it landed, just before it landed on the ground, that's the speed that a radar gun would give me. That's what's happening in real life. We're breaking it into components only so that we can do the kinematic equations, which only work in straight lines. Okay, so I hope that's enough for now. Let me know if you have questions when we get back into class together, and good luck.